Hello, my name's Mark. I'm here to help you with your GCSE and A-level maths studies. This week's topic is called partial fractions. This is aimed at A-level students beginning year 13, basically the second year of the A-level course. This is within the pure section under Algebra and Functions. The main aim of this video will be to concentrate on past exam questions and exam style questions that are likely to appear. So before we begin, I would just always like to give a bit of theory, but the main theory will be in my worked examples video I give on this topic. But just to give a recap on that, what we say is a partial fraction is when you split a algebraic fraction into easier fractions. So you have an algebraic fraction and you split it into easier fractions. But these easy fractions, most of the time in the EdXL course, will have linear denominators. Now the linear denominators are the most popular, but there may be the odd occasion where you see a quadratic denominator. The big thing is the numerators are always a lower power than the denominator. So if the denominator is linear, a and b have to be less than x to the power 1, so they have to be a constant. So they have to be a lower power than the denominator. On the odd occasion where you do get a quadratic denominator, for example ax squared plus bx plus c, just be aware you would have to put ax plus b because the numerator could be linear, because that's one power less than the quadratic. But most of the time you'll be able to split it up into linear factors on the denominator. So how do we do this? I'm going to mainly use the comparing coefficients way, but I will sub in values where necessary to make it easy on myself. So first things first, we're going to have a look at the question: express in partial fractions 5x plus 3 over 2x plus 1 x plus 1 squared. So let's begin there. So we would write 5x plus 3 over 2x plus 1 is the first linear factor on the denominator, and then x plus 1 squared. Now you can either write it as x plus 1 with a squared, or you can write it as x plus 1, x plus 1. What you notice is there's three separate linear factors here, but one of them, the x plus 1, is repeated. So this is classed as a repeated root example. You don't have an individual fraction for each linear factor on the denominator, because you'd be writing the denominator x plus 1 twice. So from my worked examples video, we realised that if you have a repeated root on the denominator, you have to write a over 2x plus 1. That's absolutely fine because that 2x plus 1 factor is not repeated. But then you have add b over x plus 1. And then the final fraction, you will get three separate fractions because there are three separate linear factors. You cannot put plus c over x plus 1, so you have to do increments of powers of 1 on the repeated factors. So x plus 1 and then x plus 1 squared. If it was cubed, it would be x plus 1 squared and x plus 1 cubed, creating three separate fractions. Each factor is raised to an increased power of 1 each time. So that's how you'd write it initially. You need to know the general form in case they don't give it you. A lot of the times in exam questions they might say express it in this form, But in this particular case, they say express in partial fractions, and you need to know the form it needs to be in. Right. The next part of writing in partial fractions is always times through by the denominator on the left-hand side. That's 2x plus 1 times x plus 1 squared. If we multiply through by that, what we will get is 5x plus 3 on the left, and that is equivalent to a times, and then the 2x plus 1 bracket will cancel, leaving x plus 1 squared. Then you will have b times, one of the x plus 1 brackets will cancel, leaving 2x plus 1 times x plus 1. Then what you have is both of the x plus 1 brackets cancel when you're times them by the c fraction, and you're just left with 2x plus 1. All we've done there is multiply through by the denominator. Now, as is always, the easiest way to find the next values is to substitute a value in for x that makes one of the brackets 0. So let's choose x plus 1 equals 0, so let's choose x equals minus 1. X equals minus 1. On the left hand side you'd get 5 times minus 1 is minus 5, add 3 is minus 2. Notice I'm putting the equivalent symbol here because this is an identity. Identities mean one side is equivalent to the other side for all values of x, not just a singular value of x that you're trying to solve. So this is why it works for every single value of x. Because you're not solving an equation, you're writing an expression in a different form. So the equivalent, like 2x plus 3, you would write 5x. That's equivalent to 2x plus 3. It works for every single value of x. Right, so minus 2 is equivalent to the a disappears because the x plus 1 bracket is 0. The b disappears because you're timesing that by 0 as well because it has an x plus 1 bracket. So what you're left with is c times minus 2 add 1. 2 times minus 1 is minus 2, add 1 is minus 1. And you would get minus 2 is equal to minus 1c, and that gives you c equals 2 when you divide by the minus 1. I'll circle that. Right. Are there any more brackets remaining where you can sub in a root? Well, yes, there are. You can 2x plus 1 equals 0, so that would be x equals minus a half. If you sub 5 times minus a half in, that'll be minus 2.5. Add the 3, would be positive a half. You would have a half is equivalent to, all the 2x plus 1 brackets now become 0. So they are 0 times b and 0 times c. So all you're left with is the a times x plus 1 squared. X is minus a half, add your 1 is a half. So you have half squared. Minus a half, add 1 is a half. Yeah, that's correct. And then you square it. So what you've got is a half is equivalent to a quarter of a. And then when you times both sides by 4, you get a equals 2. That seems reasonable at the moment. In exam questions, what they usually like to do is let the values of a, b and c be relatively kind values, but it has been known in the past to, on the odd occasion, make it fairly difficult. In the 2026 papers, all the numbers seemed fairly difficult, it seems, so just be careful. It doesn't mean you're wrong, but always double check your answers if it doesn't look particularly nice. Right, now how do we find the constant b? Well, to find the constant b, what we would do is, you could sub in x as 0 to be fair, but the best thing is to compare the coefficients, because this helps you on the harder examples as well. So compare coefficients and always choose the highest power throughout the identity. You've got no x squareds on the left, but you will get x squareds on the right. So I'll compare the coefficients of x squared. On the left hand side, you have 0 x squared. What we mean by the left hand side is the 5x plus 3 here. You have x's and you have 3 as the constant term, but you have no x squared, so you put 0. On the right hand side, you have to be a bit more careful, but if you multiply this x plus 1 bracket out, you would get x squared plus 2x plus 1. Remember, x plus 1 squared means x plus 1 times another x plus 1 in double brackets. If you multiplied this bracket out, you would get 2x squared plus an x plus a 2x is plus 3x and plus 1. And then you don't need to worry too much about the c, because c times 2x gives x's and c times 1 gives a constant, so there's no x squareds. So looking at those terms, on the right hand side, what I would say would be there are a x squareds and then plus 2b x squareds. Because we've already found our value of a, what you can do is sub in a to be 2, and you would have 0 equals 2 plus 2b. Rearranging that would give 2b equals minus 2, and then b equals minus 1. I've circled my constants, but did it say to express it in partial fractions? Yes, it said express it in partial fractions. So just to make sure we've got all the marks, what I would suggest we do at the very end is, rather than writing a over 2x plus 1, b over x plus 1, c over x plus 1 squared, we write that again, but we replace a, b and c with the values we've found. So what we would do here is put 2 over 2x plus 1. Then we would do b over x plus 1, which is minus 1 over x plus 1, because b is negative 1. And then the c, as we found, was 2 earlier, so add 2 over x plus 1, all squared. And that is how we've expressed that in partial fractions. So that is what you do to do a exam question like that, which is usually 4 or 5 marks. Not because of the difficulty of it, but because of the time and the amount of steps it takes. Remember, exam marks are not always with the amount of or the level of difficulty. It can be how long it takes to work out the answer in the exam. Which is why things like binomial expansion and partial fractions are usually worth quite a few marks, even though the complexity of the topic is not too difficult. It's more methodic, so if you learn the method you can pick up easy marks in the exam. Right, so the next exam question, what we're going to do today, is off the Edexcel papers, and it's a past exam question from June 2023, paper 2, question 10. So it's towards the end of the paper. Well, there's usually about 14 questions on an A-level paper, so 10 out of 14 is reasonably quite far near the end. But that could be because of the integration, not because of the partial fractions, but we'll see. Partial fractions usually comes up in either integration questions or binomial expansion. Very rarely comes up on its own. It's usually a part A of a question. Right, so what we're going to do here is write 3kx minus 18 over x plus 4 x minus 2. And we need to know, because it says write it in partial fractions, we need to know the general form of partial fractions. Now the nice thing is, always double check that if it's got a repeated root. This one doesn't, because x plus 4 and x minus 2 only appear once. They're not raised to another power in the denominator. But also double check if it's an improper fraction where you may need a quotient and then add the remainder over x plus 4 and x minus 2. The numerator here is a linear because it's so many x's, and the denominator here is a quadratic when you do x plus 4 times x minus 2, so it's not classed as improper. So all you would get now is a fairly simple example where you get a over x plus 4 plus b over x minus 2. The tricky thing to this question was the k involvement, but if you apply the same routine every time, if you learn the method rather than the actual numerical values that are required, you'll be able to apply that to many different types of questions. Right, so what we do is you times through by x plus 4, x minus 2 throughout. And let's see what we get here. So you'd get 3kx minus 18. You'd get a times the x minus 2 because the x plus 4 bracket cancels, and then b times x plus 4 because the x minus 2 bracket cancels. So the next step is to substitute values in or compare coefficients. It's up to you. Comparing coefficients here, because there's x's on the right hand side and that's the highest power, you'd be getting an equation with a's and b's in. So it doesn't actually help you in this case. You use comparing coefficients for the harder examples when you run out of x values to sub in. So let's substitute x equals 2. And what you'd get is 6kx minus 18. The a bracket gets times by 0, and you're just left with 6b. Or b equals, when you divide through by 6, kx minus 3. Sorry, that's my mistake. When you sub it x equals 2 to the left hand side, the 2 gets times by the 3 and you're left with 6k, not 6kx. So I'll just remove that. A big thing about maths is spotting your own mistakes. So you have to not be afraid to make mistakes, but just realise when you go back to your answer how you can check through your answers carefully. And that's where your practice makes perfect, if you like, when you're practicing exam questions. So when you divide by 6, you'd get k minus 3. Now we can sub in the root of the other bracket. In this case, it would be x equals minus 4. And what we would have is minus 12k minus 18 equals, the b bracket would get times, b would be times by 0, and you're left with minus 6a. Dividing by minus 6 actually leaves 2k. Divided by minus 6, minus 18 divided by minus 6 is positive 3. So you get a is 2k plus 3. So we've actually displayed it in partial fractions, where what we would do is write the answer at the very end. We would put 3kx minus 18 all over x plus 4 x minus 2. We would put this is equivalent to, instead of a, we would put 2k plus 3 over x plus 4. And instead of b, we would put k minus 3 over x minus 2. And that will be displaying it in partial fractions in terms of k. If we notice, it did say in terms of k, so you can't find the actual values of the constants a and b, but you can find them as an expression in terms of k. Now, what we are doing next is actually a year 13 integration question, where it may involve a bit of slightly harder integration, but I thought I would show you as an added bonus for those year 13 students revising. I know partial fractions is at the start of the year 13 course, but if you're revising for your exams, you would need to know your integration as well. So, how would you do this? It says find the exact value of k for which the integral between 1 and minus 3 is 21. Now this is why you use partial fractions a lot of the time, is because you can actually integrate the algebraic fraction easier when you split it up into partial fractions. So what you've been asked to do is integrate between 1 and minus 3 of 3kx minus 18 all over x plus 4 times x minus 2 dx. And we've been told that equals 21. Not a show that question, always double check that, because if it's a show that question you have to get your 21 as your answer, but you're finding the value of k for which this equals 21, so you know it equals 21 to start off with. Alright, so the next thing you would do is split your integral up into two separate integrals. You're integrating between 1 and minus 3 of 2k plus 3 over x plus 4 dx, and then adding the integral between 1 and minus 3 of k minus 3 over x minus 2. And that all equals 21. What I like to do is when you're integrating individual fractions like this, you would take the numerator, if it's a constant, usually it's a constant that doesn't involve x. Remember, we are integrating in terms of x. X is the variable, k is a constant. I know we don't know what k is, but it's a constant at the moment. So you can take the k out and integrate just in terms of x. The dx part tells you what the variable you are integrating with respect to, not the k. So you can take any constant other than x out. Well, x is a variable, so you can't take that out with the integration symbol. So what I would do is put 2k plus 3, the integral between 1 and minus 3 of 1 over x plus 4 dx, and the same thing for k minus 3, you can take that out of the other integral, and that's between 1 and minus 3 of 1 over x minus 2 dx, and this all equals 21. Right, this is where your second year integration comes in. Now, if you've done enough integration in year 13, you will know something called the reverse chain rule, which, if it's a function of another function, and that inner function is linear, the technique is all you have to do is integrate the outside function and differentiate and divide by the differential of the inside function. So because this is x plus 4 to the minus 1, and because the other function is x minus 2 to the minus 1, you are allowed to integrate the outside function and divide by the derivative of the inside. So here what you would do is, how would you integrate something, or in other words, what differentiates into something to the power minus 1? What differentiates into 1 over x plus 4? Well, if you know enough about exponentials and logarithms, you will know that natural log of x plus 4 differentiates into 1 over x plus 4. But I always say, when you're doing this, always remember the two-step method. You integrate the outside function, so you've integrated the power -1, and you divide by the differential of the x plus 4. Now, x plus 4 differentiates just to the number 1, but I write it just so that you get in the habit of doing it every time. Plus k minus 3, and you do the same for x minus 2 to the power -1. You integrate that so it becomes natural logarithm of x minus 2, and then divide by the derivative of x minus 2, which is just 1 in this case. But remember, these are limits, so you've got 1 to -3. There's two things I want to add. When you're integrating to a natural logarithm, always remember to put modulus signs around the x plus 4, because remember, natural logs are only defined on positive numbers, and you do the modulus sign around x minus 2. That's an important thing to remember. Mod. You get less signs. The other thing to remember is we are integrating between two limits, 1 and -3. Now, yeah, you can combine, you can put it all together as 1, but what I will do is, because I've written it separately here, I'm going to do it the individual individual fractions separately. So, if you do 2k add 3, and then times that by ln of modulus of 5, and then you're taking away ln of when you put -3 in. So -3 add 1 is -3 add 4 is 1. So it's the modulus of 1. Right, and then you do plus k minus 3, and then you times it by the when you do ln of -1, so that would get like that, and then you would minus ln of -3 minus 2 is -5, like so, and then you'd put equals 21. Right, so the next stage is to simplify this expression. So you've got ln of -1 there, you've got that's -1 minus 2 is -1, and then you've got -3 minus 2 is -5. Yeah, so that looks good to me. And then you would start simplifying. Right, remember from your natural logarithms, when you do laws of logs, take away, that would be ln of 5, or you don't have to put the modulus signs now, because modulus of 5 is just 5. Right. You can remember ln of 1 is just 0 if you want, but then you have add k minus 3 times, and then it's ln of 1, because the modulus of -1 is 1, and take away ln of 5. The modulus of 5 is 5. The modulus of -5, or you may know it as absolute value, but modulus or absolute value of -5 is 5, and that equals 21. Let's continue to simplify. So we would have 2k plus 3 times ln minus 5, or ln of 5, and then plus k minus 3, and then you're timesing it by ln 1, take away ln 5 is ln, you do 1 divided by 5 is 1/5. Right, and that equals 21. Right, the next stage is, you could write ln as a fifth or ln as -5, it's up to you. Now, how are we trying to find the value of k? Are we trying to find it in exact value form, or are we trying to find it in numerical value form, like decimal? It doesn't matter, you can do it for both here. But what I would do is factor the k's out. To do that, you'd need to collect the k terms. So 2k ln 5, and then you've got plus 3 ln 5. Then you've got plus k of ln a fifth, and then you've got -3. of learn a fifth. And that all equals 21. What we're trying to do is find the value of k. Collect the k's together. Now, just be careful here, because learn of a fifth can be written as learn of 5 to the minus 1, and that can be written as minus learn 5. So remember, learn of a fifth is the same as minus learn 5. So what you could do is put 2k learn 5 minus k learn 5. Then you've got plus 3 learn 5, and do the same thing for the minus 3 learn a fifth. You've got minus 3 and then times by minus learn 5. So that becomes a positive 3 learn 5. And that equals 21. Now we can start collecting them. 2k minus k is k. So you've got k learn 5 on this one. And then you've got plus 6 learn 5. And that equals 21. You can add the learn 5s together now because they are both the same value. Right. So all you do now is, well, you can write it in a couple of different ways, but if you want to take the, well, k learn 5 and write it as equal to 21 minus 6 learn 5, like so, and then divide by learn 5. So you've got 21 minus 6 learn 5 over learn 5, and that's actually in exact form. So all at the end, once you've simplified it, all I would do would double check the wording of the exam question. So let's go back, let's check the wording of the exam question, hence find the exact value of k. So you had to find it in logarithmic form. Okay, so that's what I've done. Not as a decimal, you had to find it as logarithm. So that was a difficult integration question where you had to simplify the logarithms, but you wouldn't have been able to do the integration without doing the partial fractions first. So that brings us to the end of this exam style questions video. Hope it was helpful. Make a start on your practice. Try and see if you can do integration type questions yourself using partial fractions. But if you're at the start of year 12, I wouldn't worry about that too much, about the integration. Just concentrate on the partial fractions, making sure how you write it in generic form, and then finding the constants A, B and C first. So if you want extra videos or live streams, they are available on my members area of my website. The live streams usually cover a quick introduction and Instagram example that are posted on Instagram previously that week that we'll go through, and then I'll open the chat to any questions that you have, GCSE, A-level maths questions, not just on the topic for that week, but any classwork, maths revision problems or homework you have, I can help you with that. Remember to keep working hard and you will be rewarded with your exams at the end of the year. Please like, subscribe or follow. It is very much appreciated on my YouTube channel. See you next time.